Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is the fourth video on indeterminate forms and L'Hopital's rule for a differential calculus course. If you haven't done so, you should probably be very familiar with the indeterminate forms watching the first video in this series. You should review L'Hopital's rule, which is the second video in this series. And we just finished evaluating limits using L'Hopital's rule on forms of 0 over 0 and infinity over infinity. But now we have an indeterminate form of 0 times infinity. And as I've mentioned previously, this is one of the most dangerous styles that students can run into in calculus, because students will often make the mistake of saying 0 times anything is 0. You have to understand, you're working with a limit. So in this limit, while it is true that as x approaches negative infinity, this number is approaching infinity because it's being squared, so it approaches positive infinity. And it is true that this number right here is approaching 0. The second number, which is approaching 0, is not identically 0. So it's not like you have 0 times something. You have something close to 0 times something, but it's not 0 times something. So you cannot assume that this will turn into 0, even though technically I think this will turn into 0. But anyhow, so this is of the form 0 times infinity. To rectify this situation or fix this situation, you want to adjust this to where it is of the form 0 over 0 or infinity over infinity. In fact, let me write that as a note right here. So you want to manipulate your expressions to the forms 0 over 0 or infinity over infinity. And the way that's done is pretty simple. It just involves a choice. One of these I'm going to put in the denominator, and one of these I'll keep in the numerator. Now the choice that I will go with for the thing that stays in the numerator is the function whose derivative will eventually disappear. That is not always going to be the case, but I would probably vie for a statement like, so my advice, leave the function whose derivative eventually will change form. Leave that function in the numerator. Now, what do I mean by whose derivative eventually changes form? Well, if you think about x squared, a couple derivatives later, it's going to be a constant. It changes from a polynomial to a constant. So the x squared is what I'm going to leave in the numerator, because eventually its derivatives will change form into a different style of function. And so that's what I'm going to do. I'm going to try to adhere to that advice whenever I have a form that is not 0 over 0 or infinity over infinity, but more specifically when it's 0 times infinity. All right, so let's go ahead and see what happens. Let's write this as equal to the limit as x goes to negative infinity. I will create a fraction where the numerator is x squared, and I will move this e to the x into the denominator. But when you do that, you have to throw a negative in its exponent. That's all you're doing, is basically putting a negative in the exponent for the other function and moving it downstairs. Be sure that these two statements are identical. And they are. If you remove the negative from that exponent in the denominator, that would be an e to the x times x squared. So these are the same statements. But now, if you take a look at this modified version of the limit, we have the numerator is approaching infinity, and the denominator is approaching e to the negative infinite power, which is e to the infinite power, which is infinity. So this is now ready for L'Hopital's rule because it's of the form infinity over infinity. And so I'll go ahead and apply L'Hopital's rule, and that'll leave us with the limit as x is approaching negative infinity derivative of the numerator is 2x. The derivative of the denominator is a negative e to the negative x. And if you allow x to go to negative infinity, that numerator will approach, well, negative infinity. The denominator will approach e to the negative infinity, which is infinity, with a negative in front of it. Now remember, I said it in the previous video, but just bears repeating. They don't have to actually have the same signs on the infinities there. They could be plus infinity and negative infinity downstairs. That's totally fine. That doesn't actually matter. As long as it's just infinity over infinity, you can use L'Hopital's rule. So we're going to go ahead and use L'Hopital's rule yet again. So I hope you've noticed that L'Hopital's rule is a theorem in calculus that can be used multiple times in a single problem. Doing L'Hopital's rule this last time, we get the limit as x approaches negative infinity. The derivative of the numerator is 2. The derivative of the denominator is a negative e to the negative x, which is just e to the negative x. And now if you allow x to approach negative infinity, you should be able to see that this denominator will approach infinity, and 2 over a massive number is 0. And there we go. Now, some people will argue, wait, but you told me that this is not 0 times infinity, so it shouldn't equal 0. And I'm going to correct you, and I'm going to say, no, I told you that's definitely not 0. That's not 0 times something. So we cannot guarantee that this will be 0. It might turn into 0, but we can't guarantee it. In this case, it happened to have turned into 0. All right, let's take another example. And this second example is actually the only other example I have in this video. But if you take a look at this, we're being asked to evaluate the limit as x approaches 0 from the right of the sine of x times the natural log of x. Now, you should note as x approaches 0 from the right, the sine is going to approach 0. But again, it's not equal to 0, it's approaching 0. The natural log of x, well, this might require you to remember what the natural log looks like as a graph. Looks like that right there. And as x approaches, as our inputs approach 0 from the right-hand side, our outputs are diving down to negative infinity. So this is 0 times negative infinity. And it's not actually 0 times negative infinity. It's something approaching 0 times something approaching negative infinity. So we have to manipulate this. Now, again, my advice, leave the function whose derivative eventually changes form in the numerator. Leave that function whose derivative will eventually change form. Leave that function in the numerator. Of these two functions, which of them has a derivative that will eventually change forms? The sine function's derivative is not going to change forms. It's going to be a trig function every time you take its derivative. There's a swap between sine and cosine. But the logarithm, its derivative will change form. So I'm going to leave that function in the numerator. And this is not the most ideal setup, but it is what it is. This is the limit as x approaches 0 from above. That's a requirement because we're dealing with the natural log. We'll leave the natural log of x in the numerator, and we'll throw that sine of x downstairs. And remember, it's sine of x raised to the negative first. By the way, this is a good time to remind you that sine of x to the negative first, this picture right here, sine of x raised to the negative first, is not this. These are two completely different things. Sine of x to the negative first is 1 over sine of x, which, by the way, is the cosecant. This is the arcsine. It's just a really bad notation for the arcsine, but it is the arcsine. So just letting you know, that exponent on this expression is not this. That's not even an exponent on the right-hand side. It's a notation. All right. So that being said, we actually mentioned something in that aside that's important. That sine of x raised to the negative first power is the same thing as the cosecant. So that's what I'm going to write here. I'm going to just go ahead and trade out because I don't want to take the derivative of a nested function like that. I just don't want to take the derivative of sine of x raised to negative first. I would rather take the derivative of the cosecant, which is the same thing. So we'll just trade that out. So no calculus has been done in this problem so far. It's like a warning on a movie. No animals were harmed in this video. All right, so if you take a look at this, as x approaches 0 from the right-hand side, we've already said this natural log is going to approach negative infinity. The cosecant, on the other hand, you might want to quickly jot out the graph or sketch the graph. Here's the sine. So the cosecant, I'll draw in blue, is going to positive infinity as x gets really close to 0. Notice I'm really trying to get you to recognize that you need to know your graphs. As x gets really close to 0, the cosecant is going to jump up to infinity. So I'll go ahead and write that in here. The cosecant will approach infinity. So we have a limit of the indeterminate form, infinity over infinity. Yes, I get it. It's negative infinity over infinity, but it's still infinite over infinite. That's all I need to know. So let's go ahead and use L'Hopital's. Oops, and I want to use black ink for that, so let me switch over. L'Hopital's rule. That'll be the limit as x approaches 0, again from the right-hand side. The derivative of the natural log is 1 over x. The derivative of the cosecant is a negative cosecant of x, cotangent of x. And again, we're dealing with x going to 0. Now, I would love to just plug in 0, but I can't. The cosecant is undefined at 0, so I cannot just say, oh, plug in 0. It just won't work. But I don't want to just jump into another L'Hopital's rule here without trying some algebra or arithmetic or trig. The algebra I'm going to do is just a slight manipulation. I'll give you a reason for this right now. I don't want to take a derivative of quotients if I don't have to. So what I'm going to do is park this x in the denominator. And maybe I'll throw the negative out front so that we kind of get things cleaned up a little bit. Also, this is 1 over the cosecant, 1 over the cotangent, so I could actually write those 1/overs as just the sine times the tangent. I find that that might be a little bit better to deal with. It's also a lot easier to see what's happening here because as x approaches 0, I could easily see it's 0 over 0. You can quickly verify that, but this numerator is approaching 0 and the denominator still is approaching 0, so it's still ready for L'Hopital's rule. Notice what's going to happen if I run L'Hopital's rule. That denominator is going to disappear. It's going to become a 1. That's beautiful. So a little bit of algebraic manipulation and a little bit of trig was used prior to doing my next step in calculus. And via L'Hopital's rule, we get a negative limit as x approaches 0, again, from the right-hand side. I will have a product rule in the numerator. That's not going to be a killer. I can totally do that. The product rule, I'll get a cosine of x times the tangent of x plus the sine of x times the derivative of the tangent, which is the secant squared of x. And this is all over the derivative of the denominator, which is 1. Not really terrible, is it? And when you look at this, you should be able to see that you could just do direct substitution. If you use direct substitution, remember that negative's hanging out. Cosine evaluated at 0, well, that's 1, times tangent evaluated at 0, that's 0, plus sine evaluated at 0, that's 0, times, don't just say, okay, now everything I know is 0, because you don't know. Maybe this is undefined. If that's undefined at 0, then we have to do some more work. But the secant squared of x at 0 is actually 1. And there we go. We now know that this is going to be 0. That is a very, very good limit, and it has a lot of meatiness to it, a lot of details that I really dig. So Again, there's examples of evaluating limits of the form 0 times infinity. The goal is really to write them as fractions. Leave the function that's going to change forms with its derivatives, leave that function in the numerator, and move everything else to the denominator.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.